Hello, thanks for watching this video. My name is Adam Baine, and I was one of the team members for the Smart Cable project. What we endeavored to do with this project was to create a self-testing musical instrument cable that basically relies on internal circuitry and electronics to transmit test signals back and forth through the cables, the tip and the sleeve of the musical instrument cable, and generates visual feedback that tells you whether or not the cable's working. So I'll just go through the presentation. So a little background, quarter-inch instrument cables. It's a very long-running design, and it uses solder joints at the end of the day. It's all about solder joints. They spontaneously fail. If you ever had a guitar cable that you plugged in, you wonder why it sounds crackly or humming, and it's not working correctly, it's probably the solder joints. They tend to fail for a multitude of reasons. In a lot of electronics, we see thermal expansion and contraction playing a role, but in a passive device like a cable, it tends to just be more like wear and tear based. So, you get high cycle counts, things being plugged in and unplugged. Sometimes, guitar players, musicians are a little rough with their gear. I've been guilty of it myself. You see people yanking on the cables and just stressing the cables in a way where they're not meant to be used. Here we have some photos of solder joints that have suffered damage. You get like this little crack, this ring around the contact, and on the image on the left, you can see that there is like separation between the actual surface of what it's soldered to and the joint itself. Here's some more images of mechanical stress buildup in solder joints. And essentially what we're looking here is mechanical overstress and high cycle count cyclic loading. We're also taking a look at stranded audio cable, how it tends to break one strand at a time. It can cause shorts. You get one of those strands touching something else it's not supposed to be touching, then you can actually short out your cable entirely. Basically, as individual strands are lost, the resistance of the cable increases, to the point where when you have one strand left and it breaks, then you got a broken cable. So failures with instrument cables, they tend to be sort of like noticed during like sound check. You'll plug into an instrument or a patch bay or pedal board, mic snake, and you'll wonder, I'm not getting signal, or I hear like crackling, humming, bad quality sound. And it's usually like a dance of like, who's got an extra cable? Do we have one that we could sub in real quick? And it's just like a troubleshooting procedure that has to happen. You have to track down the bad cable and replace it. It's a problem because this can actually impact the quality of a show. If you're an audio engineer and you have 30-40 cables being run, maybe you have a soundboard in the back of the room, you need to start running new cables back and forth. People are in their venue. If the door is already open, then people are in the venue getting beers and stuff, and it's like you feel like you're disturbing patrons, but at the same time you're trying to help the show go on. So it's really it's a tough situation to be in, and we wanted to create a solution to that. So broadly, our objective was to create a cable design that we could adapt to TRS, XLR, TS cables. We started with TS because it's easiest, because we only have 2 conductors to deal with. With TRS we had 3, XLR we also have 3. And essentially what we wanted to do was, like I said before, create a cable that has a tester built in so that we can proactively avoid cable failures before they happen. We can notice that cables are bad. If you initiate the test right before you use it and you fail a test, or if the cable fails the test, then don't use that cable, Roles and responsibilities. So I'm Adam. I did the 3D printing of the components. I designed and assembled the smart cable parts. I did all the electrical design, and I did all the programming and testing. Carl designed the stress testing machine. We both had input. We both helped with the parts for that. The calculations and computer-aided engineering analysis. He did some of the testing. He gathered components, and he did schedule. I guess we both kind of did that. So here is one of the first drawings I did for the smart cable. Basically, this is the housing that's going to house all of the electronics. And if you look closely, you can see that there are essentially spots cut out for each component. So you see a spot for an LED, there's a spot for a button, and then a spot for the microcontroller itself. I also have these rails along the sides that were initially going to be like like wire pathways to just kind of lay the wires in to have spots for that. I ended up not using that design element, but this is the first version. Threaded portion on the front for threading in a 1/4 inch barrel plug. So just some of the design objectives, we wanted to be able to initiate the test from either side of the cable, so that if you have a very long cable, like a 20 or 30 footer, where you have one end is plugged into a mic snake and the other one is plugged into a soundboard, where you wouldn't have to run back and forth. You wouldn't have to like go and unplug the cable and collect the two ends together to do the test. You can actually initiate the test from either side of the cable without removing it from whatever it's plugged into. You can just press the button, hold it down, and you'll see shortly how the test mode works. Basically, so here is an exploded view assembly of how the cable works. So this is the more updated version of the connector that incorporates a spot for the batteries to lay into. We ended up having to use 3 batteries. The initial design only called for 2 based off of voltage from the voltage data from the microcontroller's data sheet. We used PIC12F683 microcontrollers for this project, and they say they can run on only 3 volts, but under peak load, I found it to need actually about 4.5 volts, so that's what we ended up going with. So here's some more drawings. This is the more updated smart cable connector, where we have spots for the batteries. You have section views showing you kind of like each way that the parts will lay into it. I ended up having to increase the size of the spot for the microcontroller to give it room for the transistor, and I also squeezed a bunch of pull-down resistors and current limiting resistors into here also. It's all wired point to point, so there's no PCB in here. We needed to basically keep the size as small as possible so that you could conceivably use this in a patch bay sort of situation where you may have many different cables needing to be plugged in very close to each other. We'd have to minimize the amount of space, so that's why we did this sort of arrangement. Here is a strand simulation of one of the original designs. You see that the max stress is listed here on the left. You have 2 different views. Basically, this was looking to see how well the cable could withstand a lateral force from the side, like, imagining that the cable is getting like stepped on or something bumps into it, just kind of ensuring that the parts of the cable are not going to break. We actually do want to see the thing kind of like be able to sort of self-disassemble when taking a hit, because you want to actually protect the gear more so than the cable. The cable is cheap in comparison to almost anything that is plugged into. So the fact that it actually would release under a force like this when necessary is, we consider this to be a net positive so that we don't cause damage to audio gear. A lot of the times you'll see with guitars, if they get dropped or something with a cable plugged in, it actually ends up ripping the wood out. And I'll post in a picture right here of actually the exact type of situation I'm talking about. My neighbor, when I was working on this project, he actually brought over his guitar to me to take a look at. He knows I fix instruments. So he had dropped his guitar with the cable plugged in, and it totally ripped out the wood around the jack, and it all needs to be replaced and smoothed out, and basically I'm gonna have to splice in new wood, replace the jack, and it's a hollow body instrument, so I have to do all the wiring from outside the guitar and then sort of thread all the electronics in through the sound holes. It's gonna be a pretty big job. Okay, so code overview. So let's take a look at the code first. This is programmed in C in MPLAB-X. It's basically a pretty short program. It's about 140 lines, and essentially what it does is it does dynamic roll assignment. So whichever cable you press the button on, that's the one that turns on first, and it is listening for like a presence signal from the other side. So if it does not hear one, then it knows that it is going to be the sender microcontroller. So it's actually deciding on the fly that it's going to be either like the master or like, servant kind of thing. So as soon as it detects that there is no signal from the other side, then it powers on, it uses a transistor on the other side. It sends a signal to a transistor to saturate that transistor and remotely turn on the other side, so we can have the other side turn on without the button getting pressed. So like I said before, it's important to initiate the test, be able to initiate the test from either side of the cable. So that's why we did that. And then at the same point, when it saturates that transistor, it sends a high signal to that transistor. It's also sending a signal directly to one of the other pins of the microcontroller that tells it to be the receiver microcontroller. So it's actually probably a good spot to go back to this code overview slide. So yeah, so when it turns on, it configures one of the GPIOs as an input and listens for a signal. If no signal is detected, it enters center mode. It will configure one of the GPIOs as an output, pulls it high, which connects to the base of a transistor. So that's that transistor I was talking about. It will turn on the other microcontroller remotely, and then it also configures one of its pins to an output, sets it high. That's telling the other side that it's going to be the receiver. Okay, then so now the sender has turned on the other one, and it has told it that it is going to be the receiver. So then it sends two more signals, the tip and the sleeve tests, through the actual conducting path of the cable. So it actually connects directly to the same solder lugs that your tip and sleeve connections are connected to. And it sends test signals through there. It goes, sends a high, a low, and then sort of listens for like crosstalk between. So we're testing that first, that each conductor is correctly passing audio signals, and then also makes sure that they're not shorted together. So it looks to the other side to see that the sender is sending a test signal, and that we're not seeing that or rather that the tip is getting a test signal sent through it, and we're not seeing the same signal on the sleeve. That would be a short, which is bad. So it does all that. When the receiver basically receives the correct sequence of tests, it sends a signal back to the sender. It turns on its LED, and it sends a signal back to the sender that basically signifies everything's all good. It turns on both of the LEDs, and I could demonstrate that right here. And there we go. So we have debugging flashes set in here so that in the case of like during code testing, we could actually like know where each spot of the code was. So I'll do it one more time just to see. And there we go. So 2 bright LEDs means that everything is plugged in, working, and this is correctly sending audio. Okay, so here is, you just saw it on the thing. Oh, this is actually just a video of, some of the soldering I had to do for testing. These are SOIC8 microcontrollers, so the legs are extremely small. Basically had to solder these to PCBs to little breakout boards that I could plug them into a breadboard to test it. Here's a video of testing the code on the breadboard. You see the similar kind of like LED flashing, where we see essentially, my dog is barking. Yeah, basically you see the testing, how you can test from either side of the cable. There's another shot of the assembly process. And I also just wanted to do a demonstration using the cable. So I already showed you the test function of the cable where we could test it. And it turns on, right? So this is tests as a good cable. So now we'll see for sure. I'm plugging it into a looper pedal right now, which is basically just has like a guitar loop. It's like an audio recorder device. So I've recorded a guitar loop onto here, and we're just gonna make sure that it actually works. And I got a little micro guitar amp here. So you can see that it does work, and if I actually want to like test it in circuit, I could turn down the volume on here, and I can initiate the test even while everything is plugged in. If I could actually press the button. So this is actually testing in service. So let's say you're an audio engineer and you're putting on a concert, you're doing all the stuff you need to do, and you have an issue. You could go down the line of all the cables quickly, just testing all of them to rule out any cable issues before you move on to something less trivial as a troubleshooting like a source of issues. So here's a little bill of materials. Basically, this is a marginal cost per cable, so not really including any overhead or anything like the programmers or 3D printer or anything of that. This is simply what it would cost me to build one more of these cables as it stands right now. Here's a bill of materials for the stress testing machine. Here's an exploded view of the stress testing machine. This is just like assembly in Inventor, showing how some of the parts go together. Yeah, we can watch that go, basically. Yep, so they all fit together. Some more pictures of the stress machine. Drawings of the stress testing machine. Some strand, or I think these are just Inventor simulations. And then we have some hand calculations as well. Not really sure what Carl was getting at with this. So I designed and built basically the Arduino cycle counter for the stress testing machine. I'll actually just mute this. I'll just talk about it. So this is the Arduino. Basically, it's plugged into a jack that's attached to the stress testing machine that the cable is basically repeatedly ramming into this jack. And if we pause the video, if we go kind of like back a little bit, we can kind of see on the screen here what this says is how many times each conductor was connected or disconnected. So it's counting, it's doing two things. It's counting the number of insertions of the cable, and it's also testing the cable with each insertion so that we know when the cable fails. And yeah, basically it's just waiting. They haven't started the machine yet, so it's updates every 1 second with a count, an updated count. And once we start the machine here, we see there's LEDs that I put on the Arduino. This is running with the sewing machine motor. I'll put in Carl's video, and you can see, if you look at the laptop screen, you can see it incrementing with each insertion. And yeah, basically this LED flashing over here means that there is continuity detected through this cable. So essentially what this machine was meant to do was to stress test instrument cables to get them to fail so we could get a measure of how many cycle counts they can endure of like rough handling, which is, you know, typical of musical equipment.
Hi, my name is Carl Anderson, and this is my portion of the senior project. For my portion of the senior project, I wanted to do a stress machine to test the smart cables. So right here we can see our stress machine. It's mostly made out of wood that I've assembled from parts that were in my dad's garage. This main metal piece right here is a drawer slide, a spare drawer slide that came from my dad, this part right here is actually an engine to a sewing kit machine. So for my part of the project, we initially planned to create a. Initially for our project, I wanted to do two different machines to test two different types of stress. One of the stresses was it plugging in and out, and the other due to external loading on the wire. So with this machine, it was a bit of a compromise between the two, and a bit of and it exerts both these forces upon the wire. And that is all that's all because of this machine, this part of the machine right here. This is called a quick return mechanism. So a quick return mechanism is based upon this gear right here. It turns, and this pin right here pulls this arm, which pulls the overall mechanism back at a set rate, and then when it loops around, the arm moves rapidly and causes the cable to go into the jack. And right here is just a pin that a screwed down clamp onto the wire that I printed out, that I 3D printed out to secure the wire in place, while also providing some external loading on the wire.
So that's that. Data. So yeah, so this was cycle counts to failure. First, we did 5 trials with 5 instrument cables, and then also 5 trials of just the smart cable alone. So yeah, some ideas that were basically thought of from this data was that, you know, everything was underneath 30,000 cycles. The standard deviation, it kind of makes sense that the standard deviation for the smart cable was tighter than for the traditional cables. These were all different brands of traditional instrument cables. There was a Fender cable, a Proco cable, a Planet Waves, a Monster, and I forgot the last one. Whatever. Yeah, so basically the idea is that there is a lot of variance in traditional instrument cables. They're all soldered differently. They're soldered like using potentially different solder, different quality of joints, different quality of components. It sort of behooves audio engineers to choose a cable and stick to it. And we think it should be the smart cable because they have that built-in capability to test it, so you always know if it's going to work before you actually use it. So yeah, further goals. Basically, any industry that uses cables could potentially benefit from this design. You're talking networking, power transmission, even potentially undersea cables, where we have long runs of cables where clearly you don't want to go like unplugging them to test every single one. It would be great to have basically the test circuitry built into the connector itself, so that you never really have to wonder if the cable is working. And once you rule out a cable issue, you can move on to other things as far as a troubleshoot situation. Anybody who's done audio kind of is aware of the tendency for issues to be caused by cables. I'd say about 50% of issues that I encounter as a musician, as an audio guy, just as a consultant, about 50% of it comes down to cables. So if we could rule those all out with the push of a button, it saves a lot of time, and it just makes a better show for everybody. And yeah, so I'll put in Carl's videos, and yeah, that's about it. Thanks for watching the video. All right, see you next time.